The strategic environment of the mid-Cold War was defined by an asymmetric exchange of assumptions rather than information. Western aerospace intelligence built its confidence on radar tracks, thermal signatures, and extrapolated performance envelopes. Soviet design bureaus, in turn, relied on brute force engineering margins and centralized doctrine to compensate for limited materials science and constrained manufacturing repeatability. Nowhere was this tension more evident than in the aircraft that NATO designated Foxbat, the Mikoyan-Gurevich MiG-25, a machine conceived not as a balanced fighter, but as a specialized interceptor optimized for speed, altitude, and straight-line climb. Its existence distorted Western threat models for more than a decade, producing a feedback loop of fear-driven design decisions that would culminate in the F-15 program. The illusion of Soviet technological supremacy was not created by deception alone. It was enabled by the very architecture of confidence embedded in the MiG-25's design philosophy. The MiG-25 was born from a singular requirement: intercept high-altitude, high-speed intruders such as the XB-70 Valkyrie and the State Route 71. This mission profile eliminated the need for agility and low-speed handling, allowing designers to accept compromises that would have been unacceptable in a multi-role aircraft. The airframe was dominated by thick-gauge stainless steel panels rather than lightweight aluminum alloys or advanced composites. Approximately 80% of the structure was steel, welded rather than riveted, with the remainder split between nickel alloys and minimal aluminum usage. This material choice was not a mark of sophistication, but of necessity. Soviet industry in the 1960s lacked the consistent metallurgical quality control required for large-scale titanium fabrication. Steel offered predictable yield strength, tolerance to thermal cycling, and resistance to creep at the extreme skin temperatures generated by sustained Mach 2.8 flight. Structural integrity was achieved not through elegance, but through mass and redundancy. The aerodynamic configuration reflected the same logic. The wings were large, thin, and unswept by modern standards, optimized to generate lift at altitude, but structurally reinforced to survive immense aerodynamic loading during supersonic dash. Control surfaces were oversized and hydraulically actuated with minimal redundancy, a risk mitigated by the aircraft's narrow flight envelope. The engines, Tamansky R-15 turbojets, were effectively disposable. Designed for maximum thrust rather than longevity, they suffered severe fatigue cycles when operated near their thermal limits. Sustained high-speed flight degraded turbine blades, eroded combustion chambers, and shortened service life dramatically. In Soviet doctrine, this was acceptable. Engines were replaceable units, and operational longevity was secondary to interception capability. Western analysts observing the MiG-25 from afar misinterpreted these design choices. The aircraft's size, speed, and climb rate suggested advanced materials and cutting-edge aerodynamics. Radar returns indicated a massive airframe capable of extreme performance, leading to the assumption that it must be constructed from titanium alloys comparable to those used in the State Route 71. This miscalculation reshaped U.S. defense procurement, accelerating the development of high-performance air superiority fighters. The Foxbat became a phantom benchmark, a machine whose perceived capabilities exceeded its actual design limits, because no one outside the Soviet system had physically examined one. Within this architecture of confidence existed a human variable that Soviet planners considered negligible: the pilot as an autonomous decision-maker. Soviet aviation culture emphasized compliance and procedural execution over individual discretion. Training prioritized adherence to mission parameters, not personal initiative. Yet the MiG-25's operational environment placed extraordinary cognitive and physiological demands on its pilots. High-altitude interception required precise navigation, strict fuel management, and unwavering trust in ground-controlled interception vectors. The cockpit was Spartan, dominated by analog instruments and limited situational awareness systems. Thermal stress, vibration, and acoustic load were constant companions. The aircraft was not forgiving. Minor deviations could cascade into fuel exhaustion or engine failure. It was within this rigid system that Viktor Belenko operated. A trained interceptor pilot, Belenko was intimately familiar with the MiG-25's limitations and strengths. He understood the fragility hidden beneath its intimidating performance figures. He knew the narrow margins imposed by fuel capacity, the susceptibility of the engines to over-temperature conditions, and the aircraft's dependence on ground control for navigation accuracy. His decision to defect was not a spontaneous act of impulse, but a calculated exploitation of systemic assumptions. Soviet planners assumed loyalty. Western analysts assumed technological superiority. Both assumptions would be dismantled in a single unauthorized flight. The MiG-25's design philosophy inadvertently enabled this breach. Its immense speed allowed it to outrun standard air defense responses during the initial phase of the defection. Its altitude capability delayed interception, while its robust structural margins tolerated the unconventional flight profile Belenko imposed. Yet these same characteristics masked vulnerabilities. The fuel system, optimized for short interception missions, offered little reserve. The navigation suite, dependent on ground input, was ill-suited for autonomous cross-border flight. The engines, already operating near their thermal ceiling, were pushed into regimes that accelerated material degradation. The aircraft was not failing yet, but it was accumulating irreversible stress. The illusion of safety surrounding the MiG-25 was therefore dual-layered. To Western observers, it appeared as a technological marvel. To Soviet command, it was a controllable asset embedded within a tightly managed system. In reality, it was a machine whose performance was achieved by accepting extreme trade-offs, and whose operational security depended on human compliance rather than technical safeguards. The architecture of confidence was not encoded in stealth or software, but in assumptions about behavior and secrecy. When Belenko crossed into Japanese airspace, he carried with him more than an aircraft. He carried a physical contradiction to years of strategic inference. The Foxbat was no longer an abstract radar signature or intelligence estimate. It was a tangible object subject to metallurgical analysis, structural inspection, and systems dissection. The very materials chosen to ensure predictable performance under extreme conditions would soon reveal the limits of Soviet aerospace engineering. The machine that had inspired fear through speculation would be reduced to weld seams, alloy samples, and stress diagrams, its mystique dissolved under laboratory lights. This moment marked the end of an era defined by indirect knowledge. The MiG-25's architecture of confidence collapsed not through combat or mechanical failure, but through exposure. Its design philosophy, rooted in brute force reliability and doctrinal control, had succeeded in its narrow mission. Yet it had failed to anticipate the systemic risk posed by a single pilot willing to exploit its constraints. The Foxbat was fast, high-flying, and structurally resilient, but it was not invulnerable. Its greatest weakness was not material failure or aerodynamic instability. It was the assumption that secrecy itself was a structural component. The transition from static design philosophy to dynamic operational reality occurred the moment the MiG-25 left the predictable geometry of controlled interception and entered an unscripted flight regime. What had been engineered as a point defense interceptor was suddenly forced into the role of an autonomous, long-range penetrator. This shift exposed stresses that the aircraft's architecture had never been intended to manage simultaneously. The MiG-25 could tolerate extreme conditions, but only in isolation. Speed without endurance, altitude without maneuverability, power without longevity. Belenko's flight combined all of these variables into a single continuous profile, creating a cumulative stress environment that pushed the airframe and propulsion system into an abnormal convergence of loads. The flight began under routine conditions, a standard training mission that relied on ground-controlled vectors and predefined fuel calculations. The initial climb placed the aircraft into the thin upper atmosphere, where reduced air density lowered aerodynamic drag but increased true airspeed for a given Mach number. At these altitudes, even minor deviations in engine performance could result in disproportionate thermal excursions. The R-15 engines, already known for narrow operating tolerances, were subjected to sustained high throttle settings to maintain cruise speed beyond the expected duration. Combustion temperatures rose, turbine blade clearances tightened, and the fatigue cycle of critical rotating components accelerated beyond nominal assumptions. Aerodynamic loading increased in a less obvious, but equally consequential manner. The MiG-25's large wing area generated sufficient lift at altitude, but control authority was marginal. Small control inputs produced delayed responses, requiring constant correction. Each correction introduced micro-oscillations into the airframe, transmitted through welded joints rather than flexible riveted structures. While the steel construction resisted immediate deformation, it lacked the elastic damping characteristics of lighter alloys. Vibrational energy propagated through the fuselage, incrementally increasing stress concentrations around weld seams and engine mounts. This was not catastrophic loading. It was cumulative degradation, invisible to cockpit instruments. Fuel management emerged as the central constraint of the mission. The MiG-25's fuel system was optimized for rapid climb and brief interception, not sustained cruise. Consumption rates at high altitude and near maximum thrust were severe, and the absence of an advanced fuel flow computer forced reliance on manual estimation. As fuel mass decreased, the aircraft's center of gravity shifted subtly, altering pitch stability and increasing trim drag. This imposed additional aerodynamic penalties, requiring higher thrust settings to maintain speed and altitude. The system entered a feedback loop. Increased thrust led to higher fuel burn and thermal stress, which in turn demanded further thrust adjustments. Environmental conditions compounded these internal stresses. High-altitude temperatures fluctuated along the flight path, affecting air density and engine efficiency. Thermal gradients across the airframe induced differential expansion between steel panels and internal structural members. The MiG-25's design tolerated such gradients during brief supersonic dashes, but prolonged exposure introduced low-cycle thermal fatigue. Expansion and contraction cycles worked against weld integrity, not to the point of immediate failure, but sufficient to weaken the structural margin that Soviet engineers had intentionally oversized. The aircraft remained intact, but its reserve strength was being quietly consumed. Navigation without ground control represented another layer of systemic strain. The cockpit instrumentation, designed to supplement rather than replace command guidance, offered limited situational awareness. Maintaining precise heading required constant cross-checking of inertial references and visual cues, tasks made difficult by cockpit workload and physiological stress. Hypoxia risk increased as workload rose, despite oxygen system safeguards. Cognitive fatigue became a factor, not because of poor training, but because the aircraft demanded continuous correction rather than passive monitoring. The pilot was no longer an operator within a system, he was the system. As the MiG-25 approached Japanese airspace, the aircraft descended from its optimal altitude, increasing dynamic pressure on the airframe. This transition altered aerodynamic loading profiles, particularly on the wing roots and vertical stabilizers. Control surfaces, previously operating in low-density air, now encountered higher resistance, increasing hydraulic system load. The hydraulic architecture, while robust, lacked the redundancy of Western counterparts. Any degradation would have been unforgiving. The system held, but only because design margins were conservative rather than elegant. The landing phase represented the most severe concentration of stress. With fuel reserves critically low, Belenko was forced to accept a high-speed, long landing rollout on an unfamiliar runway. Landing gear, engineered for heavy mass and high descent rates, absorbed loads near their upper design envelope. Brake systems, already taxed by kinetic energy dissipation, operated at maximum capacity. Heat buildup threatened material failure in brake assemblies, yet the system performed as designed, relying on mass and thermal tolerance rather than efficiency. The aircraft came to rest not because it was comfortable doing so, but because it was built to survive abuse. By the time the MiG-25 stopped, it had accumulated a spectrum of stresses rarely experienced in a single sortie. Thermal fatigue in the engines, vibrational stress in the airframe, hydraulic loading in control systems, and structural strain in landing components converged into a unique forensic snapshot. The aircraft had not failed mechanically, but it had been pushed to the edge of its operational credibility. Every subsystem bore the imprint of a mission profile it was never meant to execute. This convergence of stresses revealed a deeper truth about the MiG-25's design philosophy. Its resilience was not adaptive, it was conditional. The aircraft excelled when operating within a narrowly defined envelope, under centralized control, for short durations. Outside that envelope, it relied entirely on overbuilt margins to survive. There was no graceful degradation, no layered redundancy designed for prolonged uncertainty. The machine endured because it was heavy, powerful, and conservative, not because it was flexible. The flight thus became a live experiment in systemic stress tolerance. It demonstrated that the MiG-25's apparent invincibility was a function of specialization rather than superiority. Each additional minute aloft consumed structural and mechanical capital that could not be replenished without maintenance intervention. The aircraft's survival was not evidence of limitless capability, but of how much excess margin Soviet engineers had deemed necessary to compensate for unknowns. When Japanese authorities secured the aircraft, they inherited not a pristine exemplar of Soviet technology, but a machine saturated with stress history. Every weld, bearing, and turbine blade carried information encoded in deformation patterns and microfractures. The MiG-25 had crossed borders, but more importantly, it had crossed from theory into evidence. The next phase would no longer concern flight dynamics or pilot decisions. It would concern microscopes, hardness tests, and the systematic dismantling of a myth built on incomplete data and unchallenged assumptions. The critical inflection point of the event was not defined by a single audible failure or a visible structural rupture. It was defined by the absence of one. The MiG-25 did not catastrophically disintegrate because its designers had deliberately traded refinement for survivability. The moment of failure, therefore, must be understood not as a sudden collapse, but as a layered sequence of systems being driven beyond their certified assumptions, each narrowly avoiding breakdown while permanently degrading itself. The aircraft survived the mission, but it did so by exhausting the hidden buffers that had been designed to mask uncertainty rather than eliminate it. The first system to enter an irreversible failure trajectory was propulsion. As the aircraft sustained high power settings well beyond doctrinal limits, exhaust gas temperatures approached the metallurgical ceiling of the R-15 turbojet. These engines were not designed with the expectation of prolonged cruise at high Mach numbers. They were optimized for short bursts of thrust, accepting severe thermal gradients as a cost of performance. During the defection flight, turbine inlet temperatures exceeded nominal limits long enough to initiate creep deformation in high-stress components. Turbine blades experienced elongation at the grain boundary level, altering blade tip clearances and reducing compressor efficiency. This did not result in flameout or immediate thrust loss, but it introduced asymmetric performance between the two engines, subtly increasing yaw moments that required constant correction. This asymmetry translated directly into airframe stress. Continuous rudder input to compensate for thrust imbalance generated localized aerodynamic loading on the vertical stabilizers. The MiG-25's tail structure, built from welded steel assemblies, resisted deformation through sheer material strength. However, welds are inherently brittle compared to riveted joints, concentrating stress at heat-affected zones. Each correction cycle imposed alternating tensile and compressive forces, accelerating low-cycle fatigue in areas that had already been weakened by thermal expansion and contraction. The stabilizers did not crack, but microscopic fissures began to propagate along weld lines, effectively recording the flight as a mechanical signature embedded in steel. Simultaneously, the fuel system approached functional collapse without technically failing. As reserves dwindled, fuel pumps operated under conditions of reduced inlet pressure, increasing the risk of cavitation. Cavitation bubbles formed and collapsed within pump housings, generating localized shock waves capable of eroding internal surfaces. The phenomenon was transient and invisible from the cockpit, yet it degraded pump efficiency and introduced pressure fluctuations downstream. These fluctuations manifested as minor variations in fuel flow, forcing throttle adjustments that further destabilized engine temperatures. The system oscillated between marginal states, sustained only by conservative design tolerances. The aircraft's flight control system entered its own failure-adjacent regime during descent. As dynamic pressure increased, control surface hinge moments rose sharply. Hydraulic actuators, sized for high-speed interception maneuvers rather than prolonged corrective input, experienced sustained load near their upper operating envelope. Fluid temperatures increased, reducing viscosity and marginally lowering actuator response fidelity. The system did not lose authority, but it lost precision. Control inputs became less predictable, increasing pilot workload and amplifying the risk of overcorrection. In a more delicately engineered aircraft, this loss of precision could have initiated a divergent oscillation. In the MiG-25, mass and stiffness suppressed instability, but at the cost of internal wear. The landing sequence concentrated all residual stress into a narrow temporal window. With fuel critically low, there was no opportunity for multiple approach attempts. Touchdown occurred at higher than optimal speed, translating kinetic energy directly into the landing gear and braking system. The landing gear struts compressed near their maximum stroke, imposing axial loads that approached yield thresholds in internal components. Brake discs absorbed thermal energy at a rate exceeding their design dissipation capacity, pushing temperatures into ranges that altered material hardness. While no brake failure occurred, post-flight metallurgical analysis would later reveal heat-induced microstructural changes consistent with thermal overstress. At no point did a single component cross the line from stress to failed. Instead, the aircraft experienced what can best be described as systemic exhaustion. Each subsystem sacrificed a portion of its remaining service life to preserve immediate functionality. The MiG-25 completed the mission not because it remained within design limits, but because those limits were intentionally conservative to offset uncertainties in manufacturing quality and operational predictability. The aircraft arrived intact, yet no longer representative of nominal condition. This distinction is central to understanding the moment of failure. The failure was epistemic rather than mechanical. The Soviet assumption that the MiG-25's performance equated to technological superiority failed the instant the aircraft was delivered intact to a foreign power. The machine had revealed its survival strategy: endure extremes by accepting damage rather than avoiding it. What Western analysts would soon discover was that the Foxbat's feared capabilities were sustained by an engineering philosophy that prioritized short-term resilience over long-term efficiency. The moment the aircraft's engines spooled down on foreign soil, the failure became irreversible. The secrecy that had functioned as a structural element of the program collapsed. Every overstressed component, every thermally scarred blade, every fatigued weld was now accessible to direct measurement. The aircraft had not broken apart in the air, but the system that protected its mystique had failed completely. From that moment forward, the MiG-25 would no longer be evaluated by inference or fear, but by calipers, microscopes, and tensile tests. The catastrophe was not that the aircraft survived. The catastrophe was that it survived long enough to be examined. The forensic phase began under conditions of controlled urgency. Japanese authorities secured the aircraft not as wreckage, but as an intact strategic artifact whose value lay in precision rather than speed. Unlike a crash investigation defined by debris fields and impact vectors, this inquiry unfolded in hangars and laboratories, guided by methodical disassembly and documentation. The MiG-25 was treated less as an aircraft than as a composite of hypotheses awaiting confirmation or refutation. Every assumption that had sustained Western threat modeling was now subject to empirical verification. The initial inspection focused on materials identification. Sections of skin were removed and cataloged, revealing stainless steel alloys rather than the anticipated titanium. Hardness testing and spectrographic analysis confirmed compositions optimized for thermal tolerance and manufacturability, not weight efficiency. The steel panels exhibited significant thickness variation, evidence of manufacturing tolerances that would have been unacceptable in Western aerospace production but compensated for by conservative structural margins. Weld quality varied, with heat-affected zones showing microstructural inconsistencies indicative of manual welding processes. These findings immediately reframed the aircraft's performance narrative. High speed and altitude were not achieved through advanced materials, but through accepting mass penalties and compensating with enormous thrust. Propulsion analysis yielded equally sobering insights. The R-15 engines were disassembled and examined for thermal damage. Turbine blades displayed creep deformation consistent with sustained over-temperature operation, confirming that engine longevity had been deliberately sacrificed for peak performance. Metallurgical examination revealed alloys capable of surviving brief thermal excursions but prone to rapid degradation under prolonged stress. Western analysts concluded that the engines were effectively consumables, designed for replacement rather than refurbishment. This discovery undermined prior estimates of sortie generation rates and operational sustainability. The MiG-25 was fast, but it paid for speed and maintenance burden and reduced engine life. Avionics inspection exposed a similar pattern of specialization. The radar system, large and powerful, relied on vacuum tube technology rather than solid-state electronics. While this limited resolution and reliability, it offered resistance to electromagnetic interference and ease of field repair. Navigation systems were rudimentary, reinforcing the doctrine of ground-controlled interception. There was no redundancy designed to support independent long-range navigation. This validated the assessment that the aircraft's effectiveness was inseparable from its command and control infrastructure. Remove the ground vector, and the Foxbat became operationally blind beyond basic dead reckoning. Structural analysis focused on fatigue and stress history. Using dye-penetrant and radiographic techniques, investigators identified microcracks propagating from weld seams in high-stress areas, particularly around engine mounts and vertical stabilizer attachments. These cracks were not indicative of imminent failure, but they documented the cumulative load history imposed during the defection flight. Laboratory testing correlated crack morphology with thermal cycling and vibrational stress, confirming that the aircraft had consumed a measurable portion of its structural life in a single sortie. The MiG-25 had survived by expending durability, not by avoiding damage. The investigation proceeded under close coordination between Japanese defense authorities and U.S. intelligence agencies, including technical specialists aligned with what would later inform analyses by organizations such as the Central Intelligence Agency. The aircraft was methodically measured, photographed, and sampled before being partially disassembled for transport. Every component was treated as a data point in a broader system-level assessment. There was no mystery left to preserve. The objective was total transparency. What emerged from this process was not evidence of Soviet incompetence, but of a radically different engineering philosophy. Soviet designers had optimized for certainty under known conditions, accepting inefficiency and whereas tolerable costs. Western aerospace culture, by contrast, emphasized efficiency, redundancy, and life cycle optimization. The MiG-25 inverted these priorities. It was reliable precisely because it was inefficient, predictable because it was overbuilt. This inversion explained why Western analysts had misread its capabilities for so long. Performance metrics divorced from material context had created a distorted image of technological parity. The forensic aftermath extended beyond metallurgy and mechanics into doctrinal implications. Analysts reassessed prior intelligence estimates, revising threat models that had assumed sustained Mach 3 capability and advanced avionics. The Foxbat could reach extraordinary speeds, but doing so inflicted material damage that limited repeatability. It was not a platform for continuous dominance, but a tool for episodic interception. This distinction altered evaluations of Soviet air defense strategy, shifting focus from qualitative superiority to quantitative deployment and centralized control. When the aircraft was eventually returned, it did so stripped not of parts, but of secrecy. Its systems had been cataloged, its materials characterized, and its limitations documented. The forensic phase concluded with a comprehensive understanding of not just how the MiG-25 was built, but why it had been misunderstood. The investigation had transformed an object of speculation into a case study in how engineering assumptions propagate through strategic analysis. The aftermath thus marked the collapse of an illusion sustained by distance and inference. The MiG-25 did not fail structurally in flight, but it failed to conceal its true nature under scrutiny. The aircraft's examination demonstrated that performance without context breeds miscalculation. The Foxbat's legacy would no longer be defined by fear, but by evidence, a recalibration that would reverberate through aerospace design and intelligence assessment for decades to follow. The systemic legacy of the defection was not confined to a single aircraft or a momentary intelligence windfall. It initiated a structural recalibration in how aviation power was evaluated, designed, and funded on both sides of the Cold War divide. The MiG-25's exposure did not merely correct Western misconceptions. It redefined the criteria by which performance, credibility, and risk were assessed in aerospace systems. The consequences unfolded across engineering doctrine, intelligence methodology, and strategic philosophy, reshaping aviation in ways that extended far beyond the Foxbat itself. In Western aerospace circles, the most immediate impact was retrospective clarity. Programs already underway were suddenly understood in a new light. The aircraft that had been conceived in response to the perceived Foxbat threat, the F-15 Eagle, was revealed to have been overmatched against a phantom rather than a peer. Yet this realization did not diminish its value. It amplified it. The F-15's emphasis on maneuverability, avionics integration, and sustained performance represented a fundamentally different response to the same strategic problem. Where the MiG-25 relied on episodic extremes, the F-15 embodied continuous dominance. The defection validated the Western approach to systems integration and life cycle optimization, even as it exposed the inefficiencies of fear-driven procurement. Intelligence practices underwent a parallel transformation. The reliance on indirect indicators, radar returns, speed estimates, and altitude envelopes was recognized as insufficient without material validation. The MiG-25 case became a canonical example within intelligence analysis of how performance metrics divorced from manufacturing context can generate systemic error. Weight, material choice, and fatigue behavior emerged as critical variables, not secondary details. The lesson was institutionalized. Future threat assessments would increasingly integrate materials science, production capacity, and maintenance doctrine alongside kinematic data. The aircraft had taught analysts that capability is not a single number, but a composite of endurance, repeatability, and human integration. Within the Soviet aerospace establishment, the repercussions were more complex and introspective. The MiG-25 had fulfilled its design mandate, yet its exposure highlighted the limitations of an engineering culture built around secrecy and centralized control. The response was not abandonment of the interceptor concept, but evolution. The subsequent development of the MiG-31 reflected an acknowledgement of the Foxbat's constraints. The MiG-31 incorporated improved avionics, better engine longevity, and enhanced crew coordination, shifting from brute force interception toward a more balanced system of systems approach. While still specialized, it demonstrated a gradual convergence toward principles that emphasize sustainability and situational awareness. At a philosophical level, the defection reframed the relationship between secrecy and safety. The MiG-25 program had treated secrecy as an implicit structural reinforcement, assuming that concealment could compensate for inefficiencies and limitations. Once that secrecy failed, the underlying assumptions were laid bare. This realization influenced not only aircraft design, but organizational behavior. Redundancy, transparency within trusted networks, and cross-validation of performance claims gained prominence as safeguards against self-deception. The cost of progress was no longer measured solely in material expenditure or pilot risk, but in the strategic consequences of miscalculation. The human factor emerged as a central theme in this legacy. The MiG-25 had been engineered under the assumption of pilot compliance as a fixed parameter. Belenko's defection demonstrated that human agency could not be engineered out of a system through doctrine alone. This insight resonated across aviation psychology and operational planning. Western air forces, already inclined toward pilot autonomy, found their emphasis validated. Soviet doctrine, by contrast, was forced to confront the vulnerability inherent in over-centralization. The event underscored that the most advanced machine remains subordinate to the decisions of the individual operating it. Technically, the Foxbat's exposure accelerated a broader shift toward materials optimization and fatigue-aware design. Engineers increasingly recognized that overbuilding to compensate for uncertainty imposes hidden costs in maintenance, logistics, and operational flexibility. The MiG-25's reliance on steel and disposable engines was effective within narrow constraints, but it highlighted the inefficiency of trading mass for predictability. Subsequent designs across both blocks placed greater emphasis on balanced material selection improved quality control, and predictive maintenance informed by fatigue modeling. Structural integrity was no longer defined solely by ultimate strength, but by how gracefully a system aged under repeated stress. The event also reshaped the narrative of technological rivalry. The Cold War had often been portrayed as a contest of absolute superiority, measured by headline figures and isolated feats. The MiG-25's forensic dismantling revealed a more nuanced reality, divergent paths towards similar objectives, each shaped by industrial capacity, doctrine, and risk tolerance. Soviet engineering was not inferior. It was optimized for a different problem set. Western engineering was not inherently superior. It was advantaged by a willingness to invest in complexity and integration. The defection transformed rivalry into comparison, replacing mythology with measurable trade-offs. In the long arc of aviation history, the MiG-25 defection stands as a case study in the limits of abstraction. Aircraft do not exist as pure expressions of performance. They exist as physical systems embedded in human organizations. The Foxbat's legacy lies in its demonstration that speed and altitude, divorced from endurance and context, can mislead both adversaries and creators. Progress achieved through specialization carries an implicit debt, payable when conditions deviate from the assumed norm. The final philosophical reflection is therefore not about betrayal or espionage, but about epistemology. The MiG-25 taught both sides that knowledge derived from observation alone is fragile. True understanding requires contact with material reality, with weld seams and fatigue cracks, with engines scarred by heat and pilots constrained by physiology. The cost of progress is not merely the resources expended to achieve it, but the humility required to reassess it when evidence contradicts belief. In that sense, the Foxbat did more than reveal secrets. It recalibrated the very framework through which aviation power was understood.